So if you remember on last class we had started with Caesar cipher. If you don't remember, we have discussed about the services and mechanisms which were already there and what are the different types of standard services and mechanisms were discussed on last day. But in fact, I told you that this is where the interesting part becomes like for us because we are starting with the algorithms. In terms of Caesar cipher, the basic principle was very simple and it was dealt with something like this, where we discussed about the generic nature, the generic structure of a Caesar cipher, which was given by P plus K mod of 26. And if you remember, I told you that here mostly the general structure is important because you will soon find for all the algorithms we are trying to find out a generic rule so that we can implement in digital. That's the basic process. Because if you manually check that if I consider that 3 steps, 3 digits should be taken into consideration while making the encryption algorithm, manually it is fine. But while we are doing it in digitally or algorithmically, then you will require the equation which is given by P plus K mod of 26. Now in that aspect also, I touched upon a very important aspect which is called as a modular arithmetic, if you remember. And I told you that why it is important. I told you that this is in a way a process in which we are trying to find out different or we are limiting the number of elements per set. And you will soon find that in module 2, as I said during the discussion on the mathematical background or the discrete mathematics involved with cryptographic algorithm, we will go into much detail, but for the time being, it is only assumed that what exactly is done by the modular 26 in this particular case. And based on that, we have touched upon this particular example of encryption, where the message hello is encrypted in a way so that now the message is WTAAT. And if you remember again, that the same thing what we are discussing over here, that here most of the time, most of the cases what we are trying to observe is this 7 is actually appearing because the plain text is 7. So basically this is my P. And K over here was given as 15. That is a key 15 as a keyword. It was the key was given as 15. So that's why 15 plus 7 was 22. So the process was we are as if doing 22 divided by 26 like this. And as there was not the remainder was 22, so it was considered that the 22 is the remainder. So this remainder is the only factor that we are bothered with. And then we go back to the table and we find out that 22 belongs to somewhere over here as W. So that's why the term came as term. Okay, so that's what we have discussed. Even you can check for the others as well. So the point is the module mod 26 does a division in which we are only focused with the remainder. Because this becomes a key ingredient to our discussion today as well. So that's why I thought of discussing once again. So the encryption, I don't think there is a problem. In fact, you don't have any problem with the decryption as well. Because that's the same thing in a different order in which we are trying to make sure that the equation here is C minus K. Okay, so in this case, what is happening? You can see the left hand side, we are actually writing the encrypted data, WTAAD. Over here, if you observe, WTAAD, this is basically the encrypted data that we are looking at. But as it is in the decipher mode, that is at the receiver, we are assuming that they are the plain text. That's why you can see at the very end it is mentioned as plain text. Because the equation in this case is we are trying to find out the message based on the cipher text over here and the key over here. So basically this always is mentioned as this should be opposite actually. This should be here and plain text should be over here. It's wrongly mentioned there. So the cipher text is in the left hand side and the plain text is what we are trying to derive because the equation is suggested in that way. So if you observe C in this case was 22. Okay, so 22 is over here. So we are doing 22 minus 15. What is 22 minus 15? 7. So the same process is involved. 7 divided by 26. Again the remainder is 7. Then hence we go back to the table and we find out that for 7 it is 8. So it is marked as 8. And it follows for the rest of the elements. So that's the basic funda for encryption and decryption. It's the same process involved on the other. Why I'm not focusing much on this because we will soon find that this process of ciphering is not that secure enough. So we we have to devise some new method of doing it. So let us take second part of it. So this is basically the block diagram associated with Caesar cipher. And if you observe on the left hand side, remember the basic block diagram that we had discussed already, in which there was a plain text, there was an encryption algorithm, and there was a key. Along with that, we were getting a ciphertext, and that ciphertext was transmitted over the channel to the receiver. Same thing is happening over here. Instead, that the encryption algorithm over here is P plus K mod of P. That's what you see. And in the right hand side is basically the receiver end, where you are getting C minus K mod of 56. That's the shown as a diagram. Just to recollect the diagram, the remapping of the diagram. So based on that, let's solve this one as a question. Let's see if we can do it. I'll give you some time for this. What does Caesar become with a shift of X? Okay, so that's the question. That's how the question are different types. Instead of the key, we have not mentioned the key directly, but we have given other information so that we can solve the question. So the first question is, what does Caesar become? Caesar is a plain text in this case. Become with a shift of F. The second question is, what key do we need to make Caesar become MKOCKB, and what key do we need to make cipher become SYFXUH? So this is basically the process involved. I give you some time in order to find the first one at least. Now, what does mean by the first letter or first equation, the first question, where we are mentioning what does Caesar become with a shift of F? Any idea what exactly is the key? F belongs to, that's why I have given the table again for you. Again, I am telling you, whenever you are trying to solve, it's always better advisable to keep the table with you, as you will be carrying your copy. So please make a note and form the table there so that it doesn't confuse you. And again, I told you that keep A as 0 and Z as 25, and don't make that mistake of changing the order. Okay, so that I have kept it as it is. So if it is F as is mentioned over here, so basically this is where F belongs. So if you observe that 5 is the key that we are taking care of. So kindly please do it for yourself. That if you consider 5 as the key, then use the encryption algorithm, because here we are doing the encryption over here. So give the encryption algorithm based on the equation I'm talking about. Based on the equation. Don't manually do it. Manually is also very easy here because the word is small. So you can do it manually, but practice it doing the C plus K, that P plus K mod of 26. So please use the equation P plus K mod of 26, this particular equation, and try to encrypt the data which is C. I'll give you 2 minutes to finish the, because that's what you are going to get in your exam paper. So hopefully this will give you a good practice of it. So please make a note of it that this is another way of asking the question without even directly giving you the key. Like the previous example, the key 15 was given, or 4 or 3 was given. But here in a different way, the same thing happens. Please try to do it very quickly. So if I happen to just note it down, to C belongs to, so the word is Caesar, SCAESAR. So this is what the plain text are. C is belonging to 2. So my P, if I go for a table like P is 2, A is 0, E is 4, S is 18. Then we have A again, which is 0, and we have R as 70. So this is my plain text. E, as always, in this case we have chosen as 5, which is constant throughout. So kindly make the arrangements and necessary addition and find the answer. If you are done with it, please let me know the type of text. I'll write it down over here. Anyone? Acha. First letter H and F J H. Okay. M W F W. So this is what the idea is. So for all the cases, I am not repeating the steps because it will be the same process involved. Okay. So hopefully this is correct. I am not exactly giving the answer right now. Before that, giving the final answers, can you do the second one also for me? What will be the number? What keys do we need? In that case also remember we have to use the decipher process. So the process should be C minus K mod of 26. Don't write the answer directly by looking at the table that this is the answer. So no, it won't be considered. So make sure you use C minus K mod of 26 and based on that you find the key. Like what will be the key. Right? So let me just give you the final answers. So these are the final answers. Again H, F, J, X, F, W. So it matches with the answer that is given. And the key in this case is used by K and the cipher also for this is Q. You can do it later as well, no problem at all. Very similar kind of question, very simple in fact this one. So you don't need to panic much, you can do it. Any doubt with this? Okay? Because the more important and interesting part is coming after this, so I'll not take much time here. Please make a please keep the question answer with you. K and Q are the two answers for the question. Can I move forward? Fine? All right. Now comes the analysis of Caesar cipher, that why we don't use it. Because we have seen that how the algorithm will work, but naturally it is not very proactive, I would say, in making the security thing happen. And that reason is that if you can see that there is only 25 keys that we can maximally take. Because each letter can have like from 0 to taking that 25, we can take only 25 possible outcomes. So what we can do, we can see the last example that I have given. That is what we call as brute force attack. Okay, that's called a brute force attack, in which one person can go on trying the different keys one after the other and find out which one gives you a fruitful result. If you observe that in the diagram itself, you have an encrypted message which is UB, A, CL, Y, whatever it is there, and it is going on using the key starting from 1. So 1, 2, 3, 4, like that is going on. And you can observe that each and every time it is getting some different result, different plain text, I would say, rather than when it is K equal to 7, the plain text is coming not very secure. So that's a meaningful sentence basically you are getting out of the information. So the point is that with respect to Caesar cipher, it is very easy to decipher the key which has been used. And as I told already that for all this algorithm, key is the important factor. Well, algorithm everyone will know, but what the key is, that's very, very important. So you can also observe the previous one also, that back calculation or reverse engineering is relatively easier in this case. You can find it out quite easily. So that's one of the major drawbacks of Caesar cipher and why it is not used. Naturally, people have evolved, the algorithms have evolved, but this is one of the reasons why it is not that popular. Right? So this is one of the cases. The second point is there a doubt here? The second doubt is, that also comes in, that in fact is one of the features you will come across with the other ciphering algorithms as well, and that is called as the frequency of English letters. So mostly what happens is that you can see the table over there. Those are the letters in the left hand side. You can see the letters and the frequency of their usage. Those are the standard, some of the standard frequency, like how many times those letters will be used in a conversation. That's a very common thing. Now what can happen is that given a particular encrypted message, okay, because this is another analysis with respect to finding out the key. So what happens is that for some cases, or rather in most of the cases where you have used the Caesar cipher, from the given cipher text, we can assume the number of frequency or the frequency of individual letters. For example, if you observe this huge cipher text which looks to be very promising and pretty secure, if you observe that I has appeared 14 times, if you go on counting one after the other, I will be of 14 times, V of 13 times, you can see it's mentioned over there, and S of 12 times. Like this has been repeated, like I has repeated 14 times in that whole message. Now what people will do, that the intruders or the third party might do, is that they can check with the table given. That means suppose it is around 14. What they can assume is that you go back to 14, what is the maximum frequency available? 12 point something. So what they can assume is that E is the letter which has been chosen as the key for the serial cipher. Now, if you go back to the table, it's given at the bottom actually for your reference. E stands where? For which key? 4. So basically, the assumption is over here that the key which has been used to decide to cipher this particular, to generate this cipher text is ideally tentatively 4. So basically, you are giving the intruder an option to find out what is it. Basically, by looking at the frequency at which the letters have appeared and by mapping to the table given, you can actually find out that what can be possibly the key. That's the basic problem with suicide. Because again the same thing, because we are using only one letter, one number out of the 25, so brute force attack is one problem, that by default he can trial kind of a method, directly you go and find out what is the key. Second point is, by looking at the frequency of generation, you can actually map it and you can assume that what can be the letter, what can be the key being used for the algorithm. This has been, that's why the heading is cryptanalysis of serial cipher. It is very easy to decrypt, rather to intrude to a ciphertext which is generated by serial cipher. So that's why it is not that popular anymore. Okay? Any doubt with this? Because we are going to add up to it. You check in the ciphertext itself, X, L, I, L, S, W, W, I, M, W, whatever the ciphertext is, number of times I has appeared. So that's 14. Now you go to the table. In the table, which frequency matches 14 times? Closest to 14. That is E. Because that's 12 point something is there. Right? So that's why, now 12.7 is E. You go back to the table, find out which can be mapped to E, which is 4. So we are assuming that the E might be 4. Which one? Yeah, this is the English language. From the English language, this is a communication. This is given. You will soon find that to avoid this, we will need number of possible combinations, and that's why we will come to that monolithic process where we will take multiple random combination of the data. We will come to that later. But for a change, the first thing that we can do is to modify the serial cipher and keep it. Okay? Any doubt? Anyone? Please. Yeah. 7. Yes. Approximately. Now that's what frequency is meaning over here. In small ciphertext, anyway you can assume very clearly, like the problem that you have solved. From the ciphertext itself, you can assume that what can be the letter. From the table you have given, small cipher, the example that I have given you over here, that's a small ciphertext. Right? You don't need a frequency to find out what is the key. You could have found out easily from mapping it correctly. But if the ciphertext, suppose it's very long and you have made sure that that's very secure using a particular key, even in that case, the brute force, if you leave out the brute force part, you can only, by looking at the frequency of occurrence of the letter, you can assume that what can be there. That's what the idea is. Right? Any doubt? Many people are discussing anything, so anything related to this? So let me add up something to ciphertext. Okay, rather serial cipher, so that it becomes a little bit more different to that of what we have. And that's let me just take this. Let's finish off this. Can you give me the plain text by considering L equals to 4, P equals to 4 for this particular message? Can you quickly do it at least some portion of it? This is the ciphertext. I am asking you to solve it so that serial cipher we can understand. That's the letter. Suppose you take around 10 odd letters from the ciphertext. 10 means you start with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up to this W you take. Just a recap of what we serial cipher have done. So up to that red colored mark, you take that as a ciphertext. You assume that 4 is the key. Because we have just now found out that 4 might be the key. Can you decipher? Can you give me the plain text by looking at it very clearly? What is the plain text you are actually getting? Very simple. This won't be the complete plain text, but at least some portion of plain text. This will be the whole message. The house is now for sale for $4 million, something like that. So you can see that very easily, even if there is a quite a big cipher text, very easily you can find out what is the plain text. So basic security and the purpose of confidentiality, integrity, and all those purpose is not right. So that's why it needs a modification. So that modification, first of the modification that comes in is called as multiplicative cipher. Any doubt? Anyone? There is some noise coming in between from the third part. Most probably you know the key, that's right. Anyway, so this is somewhere the modification on the cipher. You can see this is also very similar to Caesar cipher, except the equations are different. So here what we are doing is, for the encryption we are doing P multiplied by K. P multiplied by K, and that is why it is called as multiplicative cipher. So give me the answer for this. If you are given the same set of information of hello with the second plain text and the table that you all have referred to, what should be the output cipher text with respect to this? Following the same notation, instead of plus, you are doing a multiplication. So basically, you have to multiply 7 multiplied by 7, because here the key has been given as 7. Please do it in 1 or 2 minutes and give me the final answer of what should be the cipher using a multiplicative cipher. So the equation that we are referring to is P multiplied by K mod of 26. This is the reference. Don't look at the second part. Decipher you don't look at, because there is a specific information that is given over there. I'll inform you after that only you can complete. So just compute with the equation P into K mod of 26, where P is given by the table already from the data set and K is given as 7. So what should be the nature of it? So for this one, maybe you can do it like 7 multiplied by 7 mod of 26. So this will be for the first one, the 8th letter. This is basically 49 divided by 26. Remember, you have to only focus on the remainder. Only the remainder. Subtraction to my daughter does it. 49 minus 26 you have to do. So whatever you have to remainder will be like that. So anyone with the final answer of the cipher text? Please do it quickly. Okay, let me just show you directly. So basically it's a very simple process, just like Caesar cipher, except that the multiplication be used. But the same problem of brute force attack as well as the frequency basis attack is again possible over here. But we will not discuss that, to be honest. The part of discussion on cipher, the multiplicative cipher, is the second part, the decipher part. Is there any doubt with this? The calculation I think is pretty simple. If you ask me to now tell you how to subtract it, it's difficult for me. So these are the letters. So 23, 0, 2, 25, 25 and 20. Again refer to the table. I have not mentioned the table over here. Refer to the table, whatever the values are coming, those are X, C, Z, Z, Q. So that's the cipher text. This is another way of doing the Caesar cipher. We are almost doing the Caesar cipher, except the operation is multiplication. Now comes the different part. What happens to the deciphering part? Because in the equation there is something very unique which has been used, and I want all of you to pay attention to this, and that is called as K inverse. That's the mention over there, K inverse, and that is not the generic inverse that we come across. It is called as multiplicative inverse. Please make a note of this. K which is mentioned over there, it's not that you are doing 1 by K. It's not that inverse normally we do it, right? K inverse is 1 by K. It's not like that. It's called as multiplicative inverse, and for that understanding, I need you to focus on certain things which I am going to tell you right now. Same way, just like I did on the previous day, We will come to this multiplicative inverse in a much greater detail in second module. But in order to understand the deciphering of a multiplicative cipher, I need to let you know at least some portion of the findings of how to find out the multiplicative inverse. Okay? So I have the details with me. I think I have the slides also with me. First read it. Don't look at it in that way that it's so complex and all, because it's a discrete mathematics, so it might happen to have so many complexity on it, but I will try to explain you as simple as possible from my end. The equation that relates a multiplicative inverse is given by the first one. Please focus on this carefully. A multiplied by B is, there is a sign over there. Do you know anyone? Correct. Anyone else? What is that called? So this is not equal. This is not the equal sign that we come across. Okay? So maybe I'll just write it down over here. This triple sign is meaning congruence, right? Congruence sign. Operator we call it. What is the meaning of it? Then I'll skip out that part also. What is congruence of it? Anyone? Physically, what is the meaning? What do you mean by it? For example, what will be 12 mod 10? What will be 22 mod 10? What will be 2 mod 10? In each of the cases, result is 2. So we will say 2, 12 and 22, they are all congruent. That's the meaning of it. We don't need that right now, but that's what the meaning is. And that's what the sign is. Now what exactly is multiplicative inverse in that context? We will need to find out, suppose A is over here, the key. Focus on this. Suppose in this case, what is the key? We have considered 7 as key, right? So maybe I'll just note it down over here. So my key over here is, in this particular example, 7. The point is, the equation that we have is A multiplied by B with this part written as something of this nature. Now what does ideally indicate that there must be a multiplicative inverse of A such that this equation holds. How does it actually look like physically? We would need an element by which after the multiplication happens, whatever the product you are getting, like A into B in this case, so basically the meaning is A multiplied by B, suppose this is the product P, suppose you are getting some product value, multiplicating value. So when you divide that by 26, the remainder will be 1. That's what the meaning is physically. A multiplied by B, suppose 4 into 5. 4 into 5. What is the value? 20. 20 divided by 26. 6. Or 20 value? 20. 20 is not equal to 1. Okay. So then we can say that 5, if I consider suppose 5 is over here and we have mistakenly taken as 4 as B. So we can say 4 is not the multiplicative inverse of 5. That's kind of a meaning. Am I fine with this? Multiplicative inverse means multiplication of two elements will lead us to the remainder based on the modulo, whatever you consider to be. Okay, based on that, the final resultant residue will be 1. So in this case, suppose for example, we have 7 over here. So 7 multiplied by some value of, I would say y, just for our understanding, should be equal to 1 mod of 26. That's the way we are representing. Can you find me by a hidden child method? For the time being, we will understand that way. The hidden child method, that what should be the value of y such that the multiplication with 7 will give us a remainder provided we are dividing that product by 26. That means what I want you to do, 7 into 1, I'll go one by one, that's the way I understand. So 7 is there. So let's do this. 7 divided by 26. So I'll make a remainder table maybe here. So the remainder table is 7. So it is not valid. So 1 is not the multiplicative inverse. Same way, 7 multiplied by 2. 14. 14 divided by 26. Remainder is 14. Not equal. So you have to take, in that way you go on. You go on. Now suppose I take 7 multiplied by 10 maybe. So it is 70. 70 divided by 26. Any hope in this? I don't have the data. 50 something will come, so it is not valid. So some value is coming not valid, I would say. Now like this you go on. This is not, it is actually hit and run method, and it is not going to solve your burden of calculating multiplicative inverse. I'll come to that how, what is the algorithm behind it. But if you go on, can you tell me what can be the nearest integer value that you can consider? 11. 15. So I'll take 11 first. 77 divided by 26. Remainder? In that way, if you go, finally when you do reach at 15, it will be around 105. So 105 divided by 26. Here you will get a remainder as, but you can observe that this hit and trial method is a pretty long process. You have to go on finding out one after the another the process. But I'll come to that how to avoid it. But first let me tell me that whether you have understood the process of multiplicative inverse. What does K inverse mean? That's the first thing, because we are not discussing the multiplicative inverse at this point. We will deviate from the topic that we are discussing. So basically, whenever we are looking at multiplicative ciphering, the decipher process requires a multiplicative inverse. By that, what we mean is that the two products or the two elements integer, if you multiply them, the remainder of the division will always be 1. So that's basically an example. So let me go back to the slide once again to just show you some other example. For example, 8. Okay, for a table, for a set where Z10 is given, so modulo 10 operator. Okay, so whether is it possible to get a multiplicative inverse of 8 for that matter? Now the question comes in, sir, for which data, for which integer you are calculating? Is it for all that we can find out the multiplicative inverse? The answer is no. I'm not going to that detail because again I'll repeat it next module itself. But you can see that one of the condition I have given. The GCD of n comma a, please make a note of it since we are doing it. GCD n comma a is equal to 1 mod n. That means that if you are taking the GCD of n and a, what is n? N over here for us 26, a over here is 7. So basically you are taking a GCD of 7 and 26 and the common factor that comes in is 1. So if that is satisfied, if that condition is satisfied, that the maximum value and the key value is giving us a GCD which is 1, that is the first condition that we will check, that if there exists a multiplicative inverse of the data that we are considering. That's the law. That's the process. So first we have a, so for example here, the Z10 wala thing, maximum, the n is 10. N is 10 and my A is 8. So if you observe here, the GCD will be 2 and 2 is not equal to 1 by any chance. So we can say that Z8 will not have a multiplicative inverse in the field of Z. Understand? But in case of 7, what is happening? 26 and 7, the example that we have considered. 26 and 7 definitely will have only one only. Right? So that's why 7 had a multiplicative inverse which we calculated as 50. Continue a little bit. Clear idea? Okay. Let me take an example for the algorithm. Let's see now if we can squeeze in this problem to understand, to make your doubts a bit clearer. This is based on the algorithm on how to calculate the multiplicative inverse, because the heat and trial method is not the right way of dealing with it. Now, how do I cope about looking at the algorithm? So please make a note of this, how we are trying to do it. Should I write it over here, or I'll just give me 1 minute. Alright, please make a note of this statement. Again, I'll come back to this algorithm later. Let us just discuss about the algorithm at least stepwise. So the steps are something like this. So step 1, R1 is equal to n and define R2 as equal to a. This is the algorithm by which you don't need a hidden trial method, but the program will find out what is the multiplicative inverse. So R1 and this, along with that, the second step is define two temporary variable T1 equal to 0 and T2 equals to 1. By looking at it, you will find out the table also. So please make the steps ready and keep it with you. So T2 equals to 1. Now, third step is, if R2 is greater than 0, then perform Q equals to R1 divided by R2. Guys, please focus on this. It's very, very important. This will be again repeated in second module, but by the time, if you are aware of it, I will skip it during that period. So Q is equal to R1 by R2. Now, see the changes. After we are done with it, R will be given by another variable, which is given by, this is basically a reminder actually, R equal to Q multiplied by R2. This is just a reminder we are trying to find R. Next step is, R1 should be R2 updated by R2, and R2 should be updated by R. Just like we do for any generic program, so that we are doing, we are updating. Along with this, we will also calculate T, which will be T1 minus Q into T2. Very important step. This part, this one equation that I have referred, this is very important, because based on this only we will find out the T actually, or the multiplicative inverse. So T is this, and after this step, T1 will be updated by T2, and T2 should be updated by T. And finally, where you will stop the program? If R1 is equal to 1, then A inverse here is indicating multiplicative inverse, will be equal to, considered as T1. So whatever the T1 variable is holding at that point, that should be considered as the multiplicative inverse of the same. Please then let me know if you have written down all the steps. I'll wait for 2 minutes, otherwise if I go back to the table again, you will not be able to see the steps. So please let me know that whether you all have gone through this. All of you are having this? Right? So let me go back to the table once again. Now see for yourself if you can explain it. The question is, find out the multiplicative inverse of 11 in Z26. This Z26 means that we have the maximum n equals to 26 and my A is equal to A. Right? So see the first step. R1 equals to n and R2 is equal to A. See the table. Don't look at Q for the time being. R1 equal to 26, R2 equals to 11. Next step was T1 equal to 0 and T2 equals to 1. T1 equals to 0, T2 equals to 1. Okay, so that's why they are white color and this grey color doesn't exist for the time being. Okay, so that's the basic thing we are trying to do. Is it fine? Or should I separately do it? Or let me do it separately. I think it will be confusing for me. Let me do it over here. So let me just try the table first. So this I'll keep it as Q and I'll keep it as it is. So we have R1. We have R1, R2, R, T1, T2 and T. So these are the variables that we have to update. First step that we are trying to do, we are just substituting R1 as 26 and this as 11. Right? That was the case. What was the next step that we have considered? T0 or T0. Okay, so this is 0 and this is 1. So this is my step 1 I am trying to do. Right? What was there after that? If R2 is greater than 0, find out the quotient Q. So basically you can do it in single step itself. What they are doing? 26 divided by 11. 26 divided by 11. So your quotient is coming as 2. What will be your remainder? 4. Very good. So I am marking it like this. So filling up this table is happening something like this. So we are dividing 26 divided by 11. Quotient is updated in the left hand side, left hand corner of the table, and R is updated in the bottom of R. Now what happens to T0 and T1? Now after that, what is the step? R1 and okay, now shift from R1 to R2. So whatever the value R2 is holding, now it will be shifted to R1. So basically, this shifting is taking place over here. See for yourself whether it's possible. So based on the step, it was R1 should be now R2 and R2 should be equal to R. So that's what I did over there as an explanation. Next step was calculating T. T was equal to T1 minus Q into T2. So let me just write it down once again. T equals to T1 multiplied by Q into T2. So over here, what is my T1 at step 1? 0 minus, what is my Q? 2 multiplied by T2. What is T2? Minus 2. Minus 2 needs to be updated where? T. So this is my first step. So first step 1, if I segregate it out separately, this is my first row of value. Can you tell me the second entry one by one in the same manner? What should be the entry? R1 is updated, R2 is updated. So we will take the division of 11 divided by 4. So my quotient becomes 2 once again. Remainder 3. Very good. What should be the value of T0 and T1? Because remember, in one of the steps it was that after we have done with the updation, T equals to T1 minus Q T2, there was two steps, T1 equals to T2 and T2 equals to T. So basically, your T1 has shifted here and your T has shifted over here. This is the state that you are in right now. And also you can check that if R1 is equal to 1 or not. Is R1 1 at this point? No. R1 is holding 11. So we have to continue the loop. That's the meaning of the last line. What should be the value of T? Can you give me? Very good. So it is again the same equation we are using. So at this point, my T1 is 1 minus Q is 2 and my T2 is minus of 2. So it becomes 5. So basically the entry over here is 5. So that entry second. Any doubt over here? Can you check for the second one, third one? So again we are doing the crossover. So 4 comes here, 3 comes here, 4 divided by 3, 1 comes here, 1 comes in here. Okay. T1, T2 is updated over here, T is updated over here. Right? What will be T? Can you tell me? Just tell me. T minus 7. Correct only. Minus 7. So this is my third step. Now after this what happens? 3 comes here. 1 comes here. Quotient is 3. Remainder 0. Correct. I thought you will say 0. What will be the T1? 5. What will be T2? So I'll just do it this way. Again, repeating the same. 7. What will be my T? 26. Very good. What will be the next step? Comes here, 0 comes here. Here at this point, it checks if R1 is 1 or not, and the condition is satisfied. So what we have to do at this point, you can see that this translation has happened already. -7 and 26 has also come over here. So what was the final conclusion? The final conclusion was, if R1 equals to 1, then your A inverse or the multiplicative inverse will be equal to P1. So what P1 is holding right now? -7. So basically your A inverse should be -7. But minus or negative sign for a modulo operator, I told you in last this class, is not accepted. What we have to do? Plus 26. So you add up plus 26 over here. So the multiplicative inverse of 11 for the set Z26 is 19. So I go back to the presentation. That's been mentioned over here. If you have understood this, can you quickly do the decipher of the multiplicative ciphering that we have done? We are at this point. We have the data also with us. Suppose this one is the data. So please take the right hand side column 23, 02, 15, 25, 0. For 7 we have already calculated the multiplicative inverse as 15. Remember in the very first stage we have started off with that itself. For 7 the multiplicative inverse hidden trial method came as 15. We can satisfy that using the algorithm as well. It is there in the course material. When I'll upload, you will find it there itself. But it's not needed for the time being. So your K is K inverse. What doubt you are having? Tell me. Doubt with the table? Anything to do with this? Any problem here? This is separate question. Here the key was 11. But for the 7, I already had told you the hidden trial method where we have found out K inverse or the multiplicative inverse to 7 is 15. So my question is, if we come back to this particular question where the ciphering has been done and the cipher text is XCZZU with the corresponding numerical values of 23, 02, 25, 25 and 20. Can you do this reverse operation? P multiplied by K inverse. What I mean is, suppose for the first letter X, can you tell me what should be the writing? 23 into 15, correct? Mod of 26. So it comes around 7. What is 7? 8. What we have taken is 8. Any confusion anyone with this? No confusion means you have not either understood anything or you have understood everything. You are giving a binary answer. You should say, sir, something we have understood, some later we will understand based on the course material and the video. Anyway, just look, give it a thought, take some arbitrary values of some data, try to practice it back home. If time permits, if I don't know whether it will be permitted or not, I'll be uploading few questions on this so that you can just practice a bit. Right? So multiplicative inverse, and based on that, how we can cipher and decipher is that. Fine. Thank you everyone.